The spectral theorem is a little bit beyond the scope of the course, but not too much. And I wanted to talk about it because it really shows you how much of what we're seeing in this chapter comes just from linear algebra, from inner product spaces. The spectral theorem is actually one of the deepest part of mathematics, especially mathematical physics, with applications to all sorts of things in classical and quantum mechanics. And it's also one of the most broadly applicable areas of mathematics, with applications to all sorts of things in computer science and everything else. Yeah, it's the jumping off point for operator theory in general. So here's how it goes. So we'll start with sort of the simplest version. So if L is a self-adjoint operator on an inner product space V, then all of the eigenvalues of L are necessarily going to be real. If you have two different eigenvalues, their corresponding eigenvectors will be orthogonal to each other, and the dimension of every eigenspace is equal to the multiplicity of the corresponding eigenvalue. And so this means that you do not have any defective eigenvalues. If you have an eigenvalue of multiplicity 4, then you get 4 linearly independent eigenvectors. So this means that, in particular, you always get an orthonormal basis of eigenvectors for your space. Okay, so I'm not going to prove all of this. The third part in particular takes a bit of work, but we can definitely look at the first two. They're actually pretty straightforward. So for the first one, suppose so if LV is equal to lambda V, and so I want this to be non-trivial, so V is not 0. So this is actually an eigenvector pair. Then we can do the following computation. Let's see. So we'll take lambda, and we'll take its corresponding eigenvector VV in the inner product. And so by the linearity of the inner product, I can scoot lambda inside. And then, let's see, so then because it's an eigenvalue pair, I can replace this with LV. Since it's self-adjoint, I can move it to the other side. On the other side, I can use the fact again that it's an eigenvalue, or eigenvector. Whoops. And then on the other side of the inner product, when I pull it out, it comes out with a conjugate. Now, this means that lambda conjugate is equal to lambda, because we have if I subtract one side to the other, lambda minus lambda conjugate times this guy is equal to 0. But we agreed that V is non-trivial, so that means that this part, which is equal to norm squared V, is non-zero, because V is not the 0 vector. So that means that lambda has to be equal to its own conjugate, which means it is real. So I guess the proof ended actually right here. Oh, well, that was the proof of part 1. Let's do part 2 as well, because not only is it easy, but it's basically the same argument. So suppose we take eigenvalue lambda j, and we look at the inner product of its eigenvector with some other eigenvector. Okay, so the idea is, let's see what we have here. So if we do this, we can go, so I'm going to put the eigenvalue in on the left side. And a moment ago, you would have told me, hey, shouldn't that have a conjugate because it's going into the first slot? But we just found out in the last step that these guys are real. So putting a conjugate on it is ineffectual. It doesn't matter. So let's see. So now this is the same thing as L times Vj Vk because it's an eigenvector. And then you see where this is going. We're going to do exactly the same thing. So the next step is to take L and move it to the other side of the inner product. And then you can pull it, convert it back into lambda and pull it out. Only this time it's going to be the lambda for Vk, which is lambda k, and so now what happens? Well, again, we subtract the right side from the left, and we have lambda j minus lambda k times Vj Vk. So if we assume then that these eigenvalues are different, then that means that part's non-zero. And if that's non-zero, then it must be the case that this purple part is 0. And that means that Vj is orthogonal to Vk. Okay, there's the real end of proof. Okay, so implication. There's an orthonormal basis of V comprised of eigenvectors of L. And so if you have an eigenvalue of higher multiplicity, like say 2, okay, so there's a plane. There's 2 linearly independent eigenvectors. So you can choose them to be orthogonal by subtracting off a projection or something like that. And then you can also normalize them by dividing by their magnitude. So you can choose your eigenvectors to form an orthonormal basis. Now, if we look at the implications for this in the finite dimensional case, so for vectors in Rn, if L is self-adjoint, and self-adjoint on some subspace of Rn, then L is multiplication by some square matrix A, where A is Hermitian. So in other words, it's equal to its own conjugate transpose. So A star is the conjugate of the transpose of A. And you conjugate a matrix just by conjugating its entries. That's complex conjugate. And even better, much better, is that A looks like CDC conjugate. So this is a product of other matrices here, where C is comprised of the eigenvectors of A. So you just put the eigenvectors in as columns. And D is for diagonal, and it's the diagonal matrix whose eigenvalues, it's the matrix whose diagonal is the eigenvalues of A. There we go. And so this pretty little picture right here tells a story. So if you multiply a matrix by, if you multiply a vector by A, this is saying it's the same thing as first taking that vector and then multiplying it by C star, which converts V into the basis of eigenvectors. Then when you've got eigenvectors, then when you just multiply by D, and this has the effect of scaling each direction of the resulting vector by the corresponding amount, because that's what a diagonal matrix does. It's just a scaling. It just changes the length of each vector in the direction it's already pointing, but keeps it exactly as it is, and then converts it back into the original basis that you started in. So anyway, so that is called the diagonalization of the matrix A. Yeah. And it turns out to be super useful, like I said, for theoretical and applied purposes. But wait, there's more. So now if we look at the analog for the infinite dimensional case, so in L2, so if L is self-adjoint on the inner product space V in L2, and so this is, let me actually call it L2 of X, where X is the domain that your functions are defined on. Then there exists an operator U, actually a transformation, a unitary transformation that sends V into L2 of maybe some other space. And so U being unitary means that U star is equal to U inverse. It's often written as U star equals U star U equals the identity operator. And that means that when you see unitary, you should think, at least in the real sense, this would just be a rigid rotation. So take the axes and sort of like spin and twist them, but no reflection, no stretching, no shearing, no nothing else. So it takes one orthonormal basis to another orthonormal basis. That's a good way to think about it. Another thing that another good way to think about it is that it preserves the inner product. So if you look at U applied to X and U applied to Y in the inner product, that's the same thing as the inner product of X and Y. And that's almost equivalent to the definition. So, okay, so there's a unitary transformation, and there's some function phi on this new space. So that the operator L looks like U, and then multiplication by phi, and then U star. So this is saying exactly the same thing happens. L is unitarily equivalent. That's what this right here means, unitarily equivalent. So to a multiplication operator. And so the multiplication operator M phi here, when you apply that to the function f, that's just saying you multiply by phi. Okay, and so that's exactly what was going on back in the finite dimensional case. We're just saying, oh, you know what? We transform the basis into a new basis, a basis of eigenvectors. Here they are. And then each coordinate just gets stretched. Being. We just multiply each coordinate. Well, that's a multiplication operator right there. The first coordinate gets multiplied by lambda 1. The next coordinate gets multiplied by this, et cetera, et cetera. So this phi right here is kind of a continuous analog of eigenvalues. It multiplies the xth coordinate of f by phi x, and so on and so forth. So you can think of x as indexing the coordinates of the vector f, and each one gets multiplied by these things here. So this is kind of, this M sub phi is kind of like an infinite diagonal matrix that has an entry for every single real number. Yeah, okay, I'll just stop there. You can talk about the spectral theorem for ages because there's so many different ways to think about it, but that's good for now. Oh, and I almost forgot. This explains a whole bunch of stuff that we've been seeing. So, in fact, the Fourier transform, or Fourier series, is the diagonalization of the derivative operator. And so the Fourier transform is one specific example of the spectral theorem. Oh, I totally misspelled that. Sorry. Diagonalization. Okay, I got too excited. Yeah. So in the case when you're going back and forth between a domain that is a compact interval and a domain which is the integers, that's called Fourier series. If you're going back and forth between, and when I say back and forth here, I mean if your x is the circle and your y is the integers, then you're doing Fourier series. If x is the real line and y is the real line, then you're doing Fourier transform. But both of these are diagonalization of the differential operator.